All right, kids, we are going to start by doing the first two of these problems together so that you have somewhat of a clue. I'm sorry I'm not in class today, but we're going to do the best we can without me. So we have got, for number one, a car. I'm going to go full screen here. Cart on a frictionless track is pulled horizontally by a string with a force of 3 newtons. What's the acceleration of the cart? So I'm going to quick draw a sketch of what I imagine in my head is going on here. So we have a cart. It says that that's 2 kilograms, and there's a string attached to it, and that's pulling, let's say it's pulling to the right, and it says that that's a 3 Newton force. Okay, so I get my interaction diagram. We have the cart. Let's say I have a string over here. There's the track, of course, and then or tabletop, if you want to call it tabletop, it's whatever, and then the whole Earth. So starting with gravitational forces, we should draw gravity between the Earth and everything else in the problem. Force of gravity. Okay. Then once we're done with that, thinking about normal forces. So what is touching on, what's resting or supporting on what? And so the cart is resting on the track, which would be a normal force. That might be it. And then after that, let's see, we've got a string in this problem, and whenever we've got a string in a problem, we're probably good that we've got tension involved. So we'll say there's a force of tension between the cart and the string. So coming down to our force diagram now, what we're going to be diagramming is the forces on the cart, which are 3. We've got 3 things acting on the cart. The normal force, the tension force in the string, and gravity. So if I come here and I say that that first force, gravity. Now, here's the cool thing that we can do now that we've got this model for the force of gravity. We can say that the force of gravity on the cart by the Earth, and then we can even actually do the math and figure out what that is. We're going to get to that in a second. Let's make the rest of our diagram here. We've got the normal force, which this cart, assuming it's not accelerating up or accelerating down like I don't think it should be, this ought to be balanced by that normal force acting upward on the cart, the normal force on the cart by the track. Okay? And then we have our tension force. It just occurred to me that I haven't checked the cart by the string. I haven't checked the audio on this microphone to make sure that it's actually working. I'm just hoping it is. So if we have got those 3 forces acting here, we should be able to do some maths here and figure out what the acceleration would be. Something interesting that we can say here, this is actually not necessarily useful, but we know now that the force of gravity is 10 newtons per kilogram times the mass, which is 2 kilograms. So we could say that the force of gravity is going to be 20 newtons. I can come over here and label this as a 20 newton arrow, which means that I think that I can come up here and label this as a 20 newton arrow because those have got to balance each other out. That in this particular problem isn't actually all that useful, but that'll be the first time that you use that thing. So that's pretty neat. The next thing we're going to do here is we're going to say, all right, we have the Newton's second law equation that says the sum of all the forces must equal the mass times the acceleration. Okay? Now, this is a little bit of a hard sell, but the green arrow and the red arrow cancel each other out. They're balanced. One's down 20 and the other one's up 20, negative 20 and positive 20. So that's 0. So when we take the sum of all those forces, really the sum of all the forces is just the blue arrow. Okay? So what we're going to say is actually what we've got here is the force of tension on the cart by the string is the sum of all the forces. That is equal to the mass of this cart, which is 2 kilograms, times the acceleration. Okay? Now, we know that the tension force from up here is 3 newtons. This is 3 newtons. So 3 newtons is equal to 2 kilograms times the acceleration. So I think the acceleration should be 1.5, and now units on acceleration and something like this are going to be meters per second per second. That's number 1. So let's move on to number 2. So moving on to number 2 here. We got a man pushes a child in a grocery cart. The total mass of the cart and the child is 30 kilograms. So let's draw ourselves a cart here. We got the kid in the cart. Dude is pushing. Oh man, that's bad news. Yeah, I've done worse. On the floor here, mass of this cart is 30 kilograms. Okay, so it talks about the force of friction on the cart. It's 15 newtons. How hard does the man have to push the cart to accelerate it at 1.5 meters per second per second? So let's make our drawing here, or our interaction diagram. Man, we're going to put the cart and the kid all together in one thing here. We'll have the floor, and we'll have the whole earth on here as well. Okay, so we draw in our force of gravity from the earth to everything else in the problem. Then we are going to have a normal force between the floor and the cart, Fn. We will have a friction force between the floor and the cart. I got a little tip off about that because it says so in the problem here. And then we've got the cart is being pushed by the guy as well, so there's going to be a normal force of the guy pushing on the cart. So as we come in here to draw our force diagram for the cart, you can see that we're going to have a total of 4 forces that act on the cart. So I'm going to have 4 arrows in my diagram. There's my cart. And we can come in here right away and we can say the force of gravity acting down on this guy. Force of gravity on the cart by the whole earth. That ought to be exactly balanced because the cart will accelerate up or down by the normal force. The normal force on the cart by the floor. And then we should have the normal force. So the guy is pushing the way I have this drawn to the right. So let's say this is he's touching it, so there's a normal force. This is the guy pushing on the thing. Normal force on the cart by the man. And then we're going to have that frictional force that acts against this thing. Now, let's pause here a second. It says it's accelerating at 1.5, so I know this is going to be unbalanced. We need to be more to the right than to the left. So the force of friction on the cart by the floor is going to be right there, and it is going to be 15 newtons, it says. So we'll label the arrows that we can label now. We know that we can calculate the force of gravity on the cart is 10 newtons per kilogram times the mass of the cart. So the mass of the cart and the kid together is 30 kilograms. So that means that the gravitational force would be 300 newtons. So this is going to be 300 newtons down here. Okay? Right. Well, if that's 300 newtons down there, I'm guessing that this is going to be 300 newtons of normal force. That black force is 300 newtons because they must balance each other in order that this cart doesn't accelerate up or down. So now our question is asking me, how hard is the guy to push? That means how big is the red arrow if the acceleration is 1.5 meters per second per second. So if we take our Newton's second law equation, it tells me the total force is equal to the mass times the acceleration. Now, what is the total force here? The total force is going to be the blue arrow. That's going to be the force of friction on the cart by the floor, plus the red arrow. Again, this is a little bit of a hard sell, but the black arrow and the green arrow cancel each other out. So when we talk about the total forces, those guys balance perfectly, the black and the green do. The red and the blue force here are in competition with each other. They're going against one another. And so we know that that has to equal to the mass of the cart, which is 30 kilograms. And we want to accelerate the cart at 1.5 meters per second, which just to me seems like faster than you want to accelerate a cart with a kid in it. But hey, what do I know? So now we have this equation. We still have 2 unknowns here, but we happen to know, we actually over here, we knew that there's 15 newtons of friction. Because it's pointed to the left, let's call that negative 15 newtons, plus the pushing force of the guy on the cart is equal to 30 times 1.5 is going to be what, about 45? Okay, So that's going to be about 45 kilograms meters per second is the same thing as a newton. So 45 newtons over there. So the force, 45 newtons divided by 15 newtons. We divide both sides by 15 and we get that the pushing force, the normal force on the cart by the man, would have to be 3 newtons. Good luck.